So we are continuing with basic sciences and implications of how the cerebellum modulates cognition and how it is involved in disease mechanisms. When we were planning the conference, we divided it a little bit in anatomical and functional evidence, though there isn't really much that you can divide. Anatomy is function, and function explains the anatomy. Certainly basic sciences are the key. It's my pleasure to invite Rebecca Burwell, who actually is working together with me on cognitive mechanisms associated to the limbic system. And I actually was so happy when I found Rebecca, because we knew that we had some common interest in this and how this is associated to CSF disorders. And it's a pleasure working with Rebecca, and she's a professor of cognitive function and psychological sciences and works here at the Neuroscience Institute at Brown. And Rebecca, without further ado, please, thanks for coming, and we're looking forward to your talk.
So can you hear me? Everyone can hear me? Okay, great. So it's wonderful to be here. I want to thank Petra and Mustafa and everyone who's been involved in putting together this symposium. It's been great, and if you didn't have a chance to look at the artwork, I'm sure others have encouraged you to, but it's very interesting. So what I'm going to be talking about today is an animal model of normal pressure hydrocephalus, which I think has a lot of relevance to this conference. And I want to say right away that this wouldn't be possible without our collaboration with Petra, and that Devin Poeta, my research associate who's here, and Haley Bounds, an honors student, they were the ones that hands-on did this work. And in case I don't get to the end, I just want to acknowledge them right up front. So what I want to do today is talk a little bit about, I'm just going to briefly say a couple of words about animal models of cognition, and then about our Kaolin model, which Petra taught to Devin, and now Devin is doing most of it, or all of it, in the lab, and what we see in the model. And then the study I'll spend most of the time on is the impact of age of onset. So this is, in our study, it's when we did the procedure that led to normal pressure hydrocephalus in the rat brain. So I'll talk about the experimental design and our findings, and then if there's time, I want to talk about. I wondered what happens to ventricle size in normal aging, and does that interact with cognition? So what you're looking at here are schematics of the rodent, mouse and rat, and monkey and human brain, very rough schematics, showing the hippocampus in yellow and the parahippocampal regions, which include parahippocampal in the human brain, which is postrinal in the rodent brain, and then the entorhinal cortices. And these are the regions that we're interested in my lab. And we study hippocampus and the surrounding regions using neuroanatomy, electrophysiology, and behaving animals. And we also, the nice thing about animal models is that you can use optogenetics and designer drugs and permanent lesions, transient lesions. So we have a lot of neuroscience tools that allow us to learn about what's going on in our models. And also, I just want to make a pitch for rats. Rats are really smart. They make excellent pets, actually. If you're not ready for a dog and you want to get a rat, they're highly trainable. And if you want to see how trainable they are, if you go to clippertraining.com or do a search on amazing rats, you can see some amazing things that they were trained to do. So what we're using is the Kaolin model of normal pressure hydrocephalus. And so what Petra taught Devin to do is put kaolin, or a clay-like substance, into the cisterna magna, which causes a blockage so that the CSF can't drain and the ventricles enlarge and then push the surrounding cortices away, they atrophy. And the reasons we're interested in, perirhinal, postrenal, and hippocampus are all impacted. So this is a human brain, and then this is a control coronal section from an MRI showing the ventricles, and you can see how enlarged they are in the patients. And I think we're stuck. Hope this isn't going to happen again. Wow. Sorry. Okay. All right. So this is just someone else's data, but this is two coronal sections. This is a control animal, and this is a normal pressure hydrocephalus rat, and you can see the enlarged ventricles there. Now, what we have been doing is imaging the animals when we get to the end of the experiment, and then reconstructing the lateral ventricles. And what you're looking at here is this is the sort of skin of the rat brain, and what you can see are the reconstructed ventricles here for a control rat and a kaolin rat, and you can see, and the ventricles are quite a bit larger there. So that's working in our model. Now, the second feature, I guess you could call it the signature feature of normal pressure hydrocephalus, are gait alterations. And so Devin with Haley, they devised, it's a new apparatus where what I'm going to show you is a view from underneath of a rat walking through a tunnel, and it's set up so that, ask me if you're interested in how we do this, but it's set up so that you basically see the feet. So it's a control rat up top, and I think it's kind of cute because you can see those. But what Haley did was devise a program that actually finds the feet, locates a centroid, then identifies whether it's a left foot, right foot, hind foot, or forefoot. And then her program actually calculates a number of parameters. The main ones we use are stride length, so that's the back foot to back foot, base of stance, which is just how wide set the feet are, and then step length, which is one back foot to the other back foot. And you can see that this is the control rat for this example. Stride length is longer, base of stance is wider here, and step length is a little bit shorter, though it's hard to see. So that, again, the model is working, and we're actually going to publish this as a methods paper because if you want to buy a gait apparatus, it's $40,000 or $50,000, and you can put this one together for $100 and download the software from GitHub. So now the other thing, so those are three. She gets about 10 to 12 measures, and those are the three we use most often. But something else Devin Haley pulled out was this measure. And what this is in the stance phase, which is when the animal's feet are on the ground, she looked at the just how much time the foot was on the ground. So this is a control run, and this is a run from a hydrocephalus animal, and this is front left, front right, hind left, hind right. And this is just the time the foot is on the ground. And what you can see is that it is the kind of magnetic gait. Now for our study that I'm going to report to you, we don't have that measure. I'm not going to be able to show you that measure today because we don't have it for both groups. So now For cognition, we wanted a task that where we could test the animals repeatedly and where we didn't have to train them, because even though they're easily trainable, it does take time, and so we wanted to use a spontaneous behavior. So rats, like people and babies and monkeys, and they are interested in things they haven't seen before, so they will spontaneously explore novelty. So what we do is present a sample of 2 objects, then there's a delay, then we test the animals with another copy of one of the objects, so that one would be familiar, and a novel object. And these are the kinds of objects we use. We use, what do we call these things? Legos. Thank you. And then we do it in an open field. Now, the measure we get is discrimination ratio, so that it's the time exploring the novel minus the familiar divided by novel plus familiar. And what that gives you is, if there's no preference for novelty, the score is around 0. If there is a preference, it'll be positive, so close to 1. 1 would be never looking at all at the familiar object and spending 100% of the time. They don't do that. They look at both of them, but they look more at the novel one. And so just to show you, give you an example. So here's a sample, and then here's the test phase. And this is animal. So he's very interested in this novel object. And the effects can be kind of subtle, but they're very reliable. So it might only be, we sometimes do this with 2D images, so it might only be 10 or 15 or 20%, but it is very reliable. So the other thing about this task is that you can modify it. You can make, instead of changing an object, you can change a location of an object. That makes it hippocampal dependent. And you can make it, you can present objects A in context A, and then B in context B, and then A and B in one of the 2 contexts. And you'll get a preference for exploring the object that the animal has not seen in that particular context. So we can do context guided. That's dependent on the perirhinal and postrhinal interaction. And if it's just a straightforward object discrimination, is based on, is sensitive to perirhinal damage. So we can mix this up. Right now we are mainly using this task, although I'll just to show you about the brain circuits. This is the recently published study where we disconnected perirhinal and postrhinal cortices by lesioning perirhinal on one side and postrhinal on the other side. And what we found was that sham and ipsilateral lesions, the animals had good discrimination, and this is not different from 0. So when we disconnected that circuit, we had a deficit. So we thought that maybe hydrocephalus, because it's affecting all of these regions, would affect this simplest task. And so that's what we used, is that simple task. So in the study I want to talk about, we have 4 groups of animals. So we have 3-month-old control animals. And the control animals, they go through the entire Kaelin procedure, except they don't get the injection. So they're sham surgery controls. And they were 3 months old at the time the procedure was done. Or they were 10 months old at the time the procedure was done. So young adults or getting towards middle age. The surgery was followed by 2-week recovery, and then the behavioral testing was every other week for 10 weeks. And then, if possible, we do the imaging either right before the last test or after, depending on how we can schedule everything. And we looked at, and then we tested 5 days a week. So SOR, gait, open field, week off, and then we do that again for 5 times. So now, just to give you an example, here's the control for the 3-month-old and the 10-month-old group, and then a representative example of the 3-month-old and 10-month. The ventricles Oh, we should say that we do not have all the data analyzed for the 10-month-old group. So this is still a bit preliminary. Right now, there's actually no difference, so let me show you the data. I'm going to show you ventricle volume for the 3-month-old and 10-month-old, control, and normal pressure hydrocephalus. So there's a main effective condition, but there's no effective age of onset. And it doesn't look to me like this is going to change when we collect the rest of the data. So that's what we expect to see. We also expect to see differences in some aspect of gait. So this is basic support. So that's the stance. And what you're looking at is this is in pixels actually. Yes, look at there. And this is the number of weeks after surgery. And in this case, all we got was a block by condition effect. So, and that's probably because of the variability in the 3-month animals. And it did look to us like the gait was worse, and it does come out more in the stride length. So the stride length was much worse in the 3-month-old animals, although the ventricles are not really different. But as we were discussing at dinner last night, a lot of things are happening by other than just the changes in the ventricle size. And then, so we have age condition, age by condition, and effect here, and about the same thing going on here. So one thing that could be happening in the 10-month-old animals is compensation. Looks like all the animals are compensating a bit. Or the aged animals could just be, there could be effects of normal aging on this measure. So now what happens, this is what we were really interested in finding out about. And this is just to remind you what the SOR, I'm ahead of myself. That 0 is no discrimination. That should be, and above 0 is discrimination. And here's what we found. This is in the young group and in the older group. And here we have an age by condition trend, but if we had more animals, this would be significant. So it does look to us like there is, whereas age of onset does not seem to affect ventricle size or gait alterations. It looks like the younger animals, the younger at the age of onset, may have a bit of resilience or cognitive reserves that can help with the cognitive deficits. So I did want to talk. So one thing I want to say about this task is that it's an upstairs task. So it's a declarative, explicit task. And we heard earlier today about how cerebellum is more important, has more maybe implicit or modulatory effects on these upstairs kinds of tasks. So I see this as very complementary to the work being done in the cerebellum. And we don't study the cerebellum in my lab, but we thought, I talked with Devin and I said, well, is there anything that we can talk about? So we decided that what we could do was use our Nissl material and just sort of like an Evans ratio, just get an area at one level of all the animals and then normalize that to the brain width of the Evans ratio, so we have a sort of a normalized measure. And what we found was interesting, and we need to do the volume and we need to do some immuno or look at some other measures. But interestingly, if you just look at the area at this level, there is an age by condition interaction, so that it's very possible that the brains are just larger in these animals, and so but this seems to have popped up for some reason, and maybe at the end someone may have a comment as to whether this seems real. Of course, we have to get more data and see if we can figure out whether this is replicable. this is our cerebellar data for this presentation. Now, I said I wanted to tell you a little bit about normal aging. I studied normal aging in my graduate work, and I have colleagues that have large data sets of missile or self-stained material for young and aged animals that are characterized on a cognitive task. And I should say this data comes from Peter Rapp and his collaboration with Michaela Gallagher. They study normal aging at the NIA and Johns Hopkins. And so this is just the ventricles and the brain width that go into the Evans ratio for 3-month-old animals, 11-month-old, and old, impaired, cognitively impaired, and cognitively unimpaired. And there was no difference in the Evans ratio across the middle age and the two cognitively characterized groups. And that was actually great news for Peter Rapp and Michaela Gallagher, because what that means is that what their aging model is, they bring animals in when they're young, they house them until they're old, they test them on the water maze, which is the way they do it is highly sensitive to hippocampal impairment, and then they have, the brains go, to one person to look at hippocampal measures or immediate early genes, or they're looking at all sorts of things in a large program project. So this is good news for them, because it means that what they're looking at is a very selective deficit and not some generalized deficit that's affecting the whole brain, if that makes sense. So this is good news to them, and I was very curious about it. Okay, so just to summarize, rodents and rats especially can provide really good models of cognitive impairment. Our model shows the signature features of enlarged ventricles, gait alterations, and cognitive impairment. And it looks like, and we have to collect the rest of or analyze the rest of the data, but the deficits, the younger the onset, the less severe the cognitive deficits may be, certainly in our model. We need to do more work on the cerebellum and these. And I should say about with normal aging, there was huge variability in the ventricle size in both the impaired and unimpaired aged group. It just didn't correlate with hippocampal function. Okay, so I don't know where I stand with time. I can stop now, or I could talk a little bit about what we're going to do in the future. Am I out of time? I think I'm out of time.
Let's take questions.
Okay, so just a few acknowledgments. Devin, I already talked about, and Haley Ishansa, who is joining our CSF group, and of course I have to acknowledge my collaborators, and we're currently we have a donor funding that's administered through DIBS. So, questions?
Not so much a question, but you had mentioned in the slide where the cerebellar area was larger in the NPH, the younger ones, and just possible explanation would be potentially that area is being recruited for more of those motor skill developments, given that if you said it's more upstairs, cortical and subcortical, but potentially like when pediatric epilepsy, patients have, some area that's removed and then other areas are recruited, so you don't see the same deficits in terms of, whatever those abilities are. Potentially that could explain why you're seeing more of that, like a larger growth in the cerebellum.
So you think there does that make sense that the cerebellum the volume might increase if it's being recruited? Is there any, maybe? That's certainly something we can look at. Yes?
I have a question that has nothing to do with this, except kind of sparked by your observations. So I think it's correct that when you see somebody out of context, you're sort of taken aback and maybe difficult to recognize who that person is.
Yeah.
given your story with A and B and A, B in different contexts,
Yeah.
what is there a neurobiology to explain that?
Yes, so this is
But
my main area of
Is
work.
the setup correct, and is the question appropriate?
Say it
Is
again?
the setup correct? Is what I said a true statement about recognizing somebody, and is there data on
Yes,
that?
exactly. So that's the data I presented, and you want to know whether people, or whether that's...
Yeah.
I mean, context is very important for declarative memory because it's a retrieval cue. So, the episodes in our daily lives happen in a certain place. And when you go back to that place, then that helps you recover the memory or retrieve the memory for that episode. So context is really important. Context-guided behavior. Now, a lot of hippocampologists would say this is the hippocampus actually encodes context, but we think it happens upstream of the hippocampus. We have a lot of data on this in the postfrontal, which would be parahippocampal in the primate brain, and it makes sense because context is not only important for episodic memory; it's important for all sorts of behavior. Context-guided behavior, and so you wouldn't necessarily want to have to go all the way to the hippocampus for that representation. So we think retrosplenial cortex uses it for maybe developing context frames. Prefrontal cortex uses these representations, and postfrontal cortex for context-guided behavior. Like, for example, if I walk into my office, I know it's an office, but I also know it's my office, and so I'm going to sit down behind the desk. If I walk into your office and I sit behind the desk, that would be a failure of context-guided behavior. And so it could be that cerebellum is also using these representations of context, or modulating those representations, and that would be really interesting to know.
But I think the answer is yes, right?
Yeah.
So one more?
I really like your finding that there were no general aging effects.
Yes.
So, do you have any suggestions to us what the specific ones are that were causing your performance difference?
The performance difference in our task?
Yeah.
So,
As a function of aging.
in terms of aging? Okay, so the question is, so I showed normal aging data where there's huge differences in ventricle size, but no effect on hippocampal dependent cognition. And what we show in our, and we know from a lot of data on normal aging that some people, so normal aging, unimpaired people that do not show cognitive impairments, it's not because their brains look just like the young animals, it's because they are compensating in some way. And the people and animals who show the impairments are not able to compensate for age-related changes. Now, I think in the 3-month-olds, which are actually about maybe 6 months old at the end of the study, or in the 10-month-old, which are more like 13 or 14 at the end of the study, the younger animals are just able to use resources to compensate that aren't necessarily available to the older animals. Does that answer your question?
Partially, yes.
Okay, well, maybe we can talk more during a break.
Well, I would, if I may.
Yeah. Uh-huh.
I had always, when I looked at the results, I had always thought that aging is making you prone to, or more susceptible to cognitive deficiency. If you think of aging with a breakdown in blood-brain barrier, or accumulation of tau and amyloid, just as a fact of aging, and then the hydrocephalus on top of it, then that gets you, downhill. So, and I was talking earlier about microglia, which I also think are, I think there's data there that supports that microglia activation with aging is facilitated because the aging brain is in a kind of like pro-inflammatory stage. So I was looking at it from so that's why I thought that our old rats, are going south quicker. But that is all like now from looking at from the translational. So I take the human observation back to the rats and trying to explain that, And that is something that I also want to mention to the medical students. How this is. So my excitement was, I thought I was excited like a child when I saw that the rats walking like what I see in the humans. I couldn't believe what that means, that for a physician, that sees the patients for decades, and then you have a model, that does the same thing with the feet. So then you think this is something unique, across, lives, across systems, and that's the brain, and not just the human brain. So that leaves you with a lot of excitement. So I want to encourage you, to do translational work. So that's a good example amongst others.
And I should say that, Devin, as we are trying to look at these tasks in the context or framework of normal aging, and it's just really hard to get the animals even at 10 months old so that we can keep them. So we have 6 animals at 28 months that we started testing at 3? Okay, so it's really hard to get those animals, but we are trying to see what these animals do in our task. But thank you again for your attention, and you can talk to me.